Good morning, good afternoon, good evening, everyone. And thank you for attending the second day of our annual workshop on survey methodology. I am Alexandre Barbosa from the Regional Center for Studies on the Development of the Information Society, Cetic.br, at the Brazilian Network Information Center. This event is jointly organized by Cetic.br and the National School of Statistical Science linked to the Brazilian Institute for Geography and Statistics, IBGE, our national statistical office. For those who were not able to join us yesterday, I just want to mention that we had two very interesting sessions on data collection, innovation, and dissemination for estimation of ICT indicators and price indices. And in fact, we yesterday already touched the surface of today's topics of big data, but today we are going to deep dive on big data in official statistics. We will discuss new methods based on alternative data sources and how to meet quality standards. We also discuss the use of machine learning as statistical methods, among other topics in the domain of official statistics. So without any further ado, I would like to invite Professor Pedro Nascimento Silva from the National School of Statistical Science, who will introduce our guest speakers and moderate today's webinar. I wish all of you a very interactive and productive webinar. And thank you very much, Professor Pedro, for having accepted our invitation to moderate today's webinar. It is really a great pleasure to have you here with us today. Please, you have the floor. Thank you.
Thank you very much, Alexandre. It's a pleasure and an honor for me to be moderating your session today. So good morning, good afternoon, good evening, everyone. I again welcome you to this second day of our NIC.br workshop on survey methodology, which is in its 11th edition. Due to the pandemic, we had to conduct this year's webinar once again entirely online through a series of webinars addressing the theme of innovation and trends on ICT data production. We are looking forward that in 2022, we will be able to return to the traditional face-to-face format and welcome all of you in São Paulo, Brazil. We all know that the COVID pandemic has severely affected the data collection activities, impacting production of public and official statistics around the globe. All national statistical offices and similar data producers face challenges to maintain their outputs through traditional methods. Face-to-face data collection became very difficult, if not impossible, in many parts of the world. Hence, innovation, cooperation, adaptability were key to enable them to continue producing reliable data and information to meet users' needs. The pandemic crisis has also highlighted the vital role digital technologies play in connecting people and allowing institutions to enable their continuity of labor, education, public services, commerce, etc. This 11th edition of the NIC.br workshop on survey methodology will showcase and discuss innovative methodologies and explore new data sources to address complex issues in the domain of ICT data production to bridge data gaps. The disruption on data production caused by the COVID-19 crisis certainly presented challenges, but also created new opportunities. Some trends on the production of statistics will be addressed by speakers in today's session. Before we start our session, I'd like to remind us of the rules for online interaction in this virtual workshop. The format of today's webinar is composed by two sessions with keynote presentations of 50 minutes plus Q&A sessions of about 15 minutes each. After the first keynote presentation, we will have a 15-minute comfort break after the Q&A session for the first keynote presentation. Please note that simultaneous translation is available for Portuguese and Spanish and English. Please select the preferred language in the globe icon. Please check that your microphone is always muted once workshop starts. And we ask you kindly to use the chat area for raising questions or comments to the speakers. I will read them and pass them on to the speakers. If we have time, I may be able to open the floor for some of you to present your questions orally. Please note that the meeting will be recorded for report writing purposes. And if you stay on the meeting, you are implicitly agreeing to this recording. Now we will start our second webinar entitled Big Data and Official Statistics. I'd like to give the floor to Marco Putz, who is a methodologist and data scientist at Statistics Netherlands. His research focuses on the usability of big data and machine learning in official statistics. Marco, you have 15 minutes, and if needed, I will interrupt you about 5 minutes before your time is up. So please, Marco, the floor is yours.
Yeah, thank you very much for the nice introduction, and good morning, everyone. Now I have to share my screen. There we go. Okay, here we go. The session of today is called Big Data and Official Statistics, and the main part of this talk will be on using machine learning algorithms as statistical methods. And a lot of people working in data science think that using machine learning is quite straightforward. But as always, we methodologists always think differently, and the way I found out it is different from just using the methods I will present here. So official statistics have a very clear quality framework, and besides all the time-related dimensions of quality of official statistics, I show you here the most important, actually all of them, the dimensions which statistics have to be fulfilled before you can call it an official statistics. It has to be relevant, it has to be accurate. We don't like bias in our statistics. It has to be accessible, it has to be clear, it has to be coherent, and it has to be comparable. And at the moment that you have statistics which have to fulfill these quality standards, it's actually obvious that the methods itself that you use also needs to meet these quality standards, and somehow we have to deal with that. So we have to make sure that these methods are at that point. And most of the methods that we used earlier actually were quite straightforward when it was about making decisions and stuff like that, and it was quite easy to get them to these quality standards. But now we are using machine learning, and with machine learning it is quite hard. One of the things that happens, for instance, is that when you use a machine learning algorithm, most of the people actually don't know anymore which assumptions are underlying the methods. I mean, for a statistical methodologist, it's really really bad if you have a method and you are going to use it without knowing which assumptions you. But in machine learning, it's quite normal to have this, and somehow we have to deal with this. We have to deal with the fact that we have these methods and that you can apply them, and somehow the model should be relevant, accurate, accessible, clear, coherent, and comparable. So how do we do that? I will tell this in the following steps. First, I will say something about the research method most data scientists use, which is actually induction. Then I will forward to machine learning itself. Then I will come to classification. I will zoom in on classification. Then I won't repeat the title of this part. It's a long one, and it will be clear at the moment that I start talking about it. It has to do with the fact that when you have human annotated data, it's actually restricting the performance of your machine learning algorithms. Then I will say something about the representativity of training sets, and I will finish with explainable AI. But first, induction and deduction, and I also added there abduction. I come from the field of visual sciences, and within visual sciences, it is really normal that researchers start with wondering about something. And the thing I wanted to illustrate here is they wonder about this cafe wall, which is somewhere in the United Kingdom. And because it looks like the tiles are not straight, are not in a straight line. They are actually banded. And whereas when you take a ruler, then you will see that actually all the lines are straight. So this is the starting point of research within the visual sciences. It's just an observation. And a lot of research starts like this. For instance, here, Müller-Lyer illusion is something like this. This line has the same length as this line. Then the squintillizing grid illusion, you see black dots appear in the middle of the Y dot when you look around. The cafe wall illusion I also explained, but the nicest one are paintings of M.C. Escher, which are actually impossible. When you follow the water, then it enters here, it goes here and here and here, it streams down, and then at a certain moment you are at the top of the building again. So somehow we look at local cues and not at the complete picture. So and that's why we don't see this strange effect. We don't see that strange effect. So somehow. And this also leads to a lot of research about local and global perception. So what you do in those fields is that you start inductive. You start with an observation and you try to recognize some patterns in that observation. You form a possible hypothesis and you form a theory. And in my opinion, you shouldn't end there. At the moment that you end here, inductive research is really like a lot of methodologies say not good. So actually, I know machine learners who actually stop up here. They have their observation and something, they come with a pattern and they stop with everything and say, okay, I have a model, but at least you have to form a theory, and a data scientist forms a theory. But then it comes, then you have to generalize from that theory. Then you have to form a new hypothesis due to in the next deductive step. You have to gather new observations, maybe more data, maybe look in a different way to the data, and you have to come to an interpretation. And this one looks around as long as it is necessary. Within philosophy, this is called scientific realism. So you know that there is somewhere a ground truth out there, but you don't know what the ground truth is exactly. And the more you investigate on the ground truth, the closer you get to the ground truth. And that is actually how you should do research in data science, in my opinion. So inductive research is not bad at all, but you should go further than that and come in that deductive cycle at a certain moment and make sure that you deepen your knowledge about what you're investigating. So the next slide is on machine learning. And machine learning is a subfield of artificial intelligence. Now, artificial intelligence started as a field where people tried to mimic human intelligence, and they were not really successful in that. But some of the things that they developed within artificial intelligence are quite successful. And one of the areas is machine learning. Roughly, we see in machine learning, we can see in machine learning unsupervised learning and supervised learning. Unsupervised learning are clustering techniques, for instance, and supervised you can have classification and regression. And I will focus here on classification because we see that within big data, when we are looking at texts, when we are looking at images, we are always trying to classify the text and the images. We don't do that much regression. It's mostly classification that we do in the field of big data. So I will focus on classification in this presentation. Now let me explain classification. I mean, you all know logistic regression. I don't have to explain that, but just see if we can get a grip of classification. For me, classification is the following problem. I have somehow I have a set of features on something, and I have a function that maps those features onto a score. And on the x-axis here, I plotted the score, and on the y-axis, I plotted the proportion of times, the number of times that such a score appears in the data set. So I have a set of features. I have a function which maps the set of features, the features on a number, which is a score, and I plot the score against the features. I have two categories in this case: the negatives and the positives. Let's call the red the negatives and the green the positives. And the goal is to find somehow some score which separates the positives from the negatives, and that's what you see here. Many of the school book examples of machine learning, you always see that these two are completely separated. So the negatives and the positives are completely separated. And actually, I found a lot of data sets on the web, and they said that they were for educational purposes, but I didn't learn anything from them, because the first model that I always use, and that's just logistic regression, when I apply it to these data sets, I get a perfect segregation of the negatives and the positives. So it's actually, I hope when you are studying machine learning in modern times that you will have some more challenging data sets, because they are really not challenging. So, but what you see in reality is something like this. When you are classifying texts, like Pete Das will show in the next presentation, when you are classifying images, you will find a score which looks like this, where there is a large overlap between the negatives and the positives. And somehow you have to decide where you choose that something is positive and negative. And you can do that with introducing a threshold. For instance, the most optimal threshold in this case is the one which is at the intersection of the two distributions. So you can actually prove that. And as someone who worked in visual sciences, in psychophysics, I actually proved it a lot of times when I was giving lectures. So that's one place where you can leave it. But if you really have to be sure that all the negatives are in your data set are classified in the right way, then you actually have to move the threshold up. And this is what machine learners call high precision and low recall. So this is one possibility. The other possibility is that you want to make sure that all the positives are in your data set. That is when you move the threshold really down. So so this is the way we are looking at these algorithms. So, but sometimes problems appear, and these problems have to do with bias, like the title already says. And for that, I have a thought experiment. So suppose I have 99 red marbles and 1 green marble, and I want to have a model that predicts the color correctly in 99% of the cases. So I'm blindfolded. I take out one marble, and I have to say in 99% of the cases correctly which marble it is. And maybe it is nice to let people over the chat give us the model which actually does this. So it's actually not really a difficult question, but yeah. And I cannot see the chat, so I hope Pedro is going to help me.
For now, we still don't have anybody replying, but somebody now said all red.
Yeah, that's actually the right model. Yeah, yeah. And you take the model when you always say that the marbles are red, then everything works. But suppose I throw in 98 green marbles extra, then the model actually doesn't work anymore. Then actually the there are 50% red marbles and 50% green marbles. And the model, which was working really well at a certain moment, doesn't work anymore. So somehow the predictive power of the model just disappeared. I always like to look at classification algorithms using a Bayesian ideal observer model. It's something that also comes from perception. It's coming from psychophysics, and is also adopted by decision theory. And what it says here is that the probability of a certain class given a feature vector is equal to the probability of the feature vector given a class times the probability of the class, this is the prior, divided by the probability of the feature vector. And in our case, we didn't have any information about features because I was blindfolded. So this is actually a uniform distribution. The predictive power of the model is completely dependent on the proportion positives and the proportion green marbles in the jar. So it's completely dependent on this one. The fact that I know how many red and how many green marbles are in the jar makes that the model works. It doesn't have to do anything with this part, which is actually the intelligent part of the model. So somehow we have to deal with that, especially when you're making official statistics. This can be your target variable, the proportion positives in your population, the proportion people having COVID in your population, the proportion men and women in your population, the proportion innovative companies in your population. This is actually your interesting variable, and it's here in the prior. So how can these models ever work? So that's the question that I started to ask myself last year, and I came to a conclusion. People at Statistics Now didn't hear from me for a couple of months, and I finally came to the conclusion, and it has to do with the PX here, so the probability of the probability distribution of the features, and what I can do is actually define this probability like this. And what I can do is just by just creating a maximum likelihood estimator of the probability of positives in there, and then I can actually do something good about it. I think that the Bayesian ideal observer model is actually a very good model to model a lot of things. So I use it now to model bias, but I'm also looking at other things that can happen with that data, with those models, to put it in this model. It looks very much like a naive Bayes method for the machine learners with us, but the thing is that I'm not using it to predict the model itself. Actually, the model that I used for the bias is actually I don't use the feature vectors here, but I just use the scores of other machine learning model in here. So I use it the other machine learning model as a dimension reduction step. So this is actually the thing that I do. And to show you how big the effect of that bias is, just that I introduced, that I showed you is in the data. I have this slide, and it's about the left panel. I created 3 data sets, one with 25% positives, one with 50% positives, and one with 75% positives. And what you see is that when I vary in the test sets the proportion positives from 10% to 90%, you see actually that there is always a big bias in there when the proportion in the test set is not equal to the proportion in the training set, and that's really a problem. The maximum likelihood method that I created actually solves this problem. So you don't have that bias anymore. So yeah, so I think this is really an important step forward in using machine learning algorithms. That you see that there is actually somewhere a problem when using these methods. You cannot just use it and assume that everything is correct. So there are two ways of using these classifiers. Wait a minute. I'm sorry, my iPad is disturbing me. So Siri started to think that I was asking a question to it. So so there are two ways of looking at these methods. One for classification and one for quantification. In the classification method, we use thresholds, or maybe in argmax at the moment that we have more categories. When you use deep learning, very often softmax is used, which is actually also a sort of argmax. And another way of using the results of the classifier is actually calculating the expected value by adding up the probabilities. One is called classification. The other one is called quantification, and the field of quantification is actually developing at this moment. So people are looking more and more at quantification methods when using machine learning. The problem is also when, suppose you have a NIC code and you want to automatically classify companies, and you use a machine learning algorithm, a classifier, and you're going to threshold it, then you know that you do a lot of misclassifications, and you are going to you're going to take all those errors with you in the end result, and that's actually something you don't want to do. So so somehow you have to find other ways of using these classifiers when using them in a statistical process. Okay, are there any questions until now? Because then I can drink a little bit water again. So
not yet, Marco. But
okay.
If somebody throws a question, I'll let you know. Okay,
perfect. And there is that curious title I had in my introduction already, the asymptotical behavior towards annotated data. And it's actually something that I started to observe when a colleague of mine was humanly annotating data, which was not really clear, even not for the annotators itself. And a lot of people said that they didn't know in what category the item actually should be. And I started to think, hey, wait a minute. If we have a human annotator who isn't sure about the class in which a certain item is, then we are actually going to learn that to a machine learning algorithm. So somehow we have to deal with that. So the problem starts within human perception again. And in the paper Pete and I wrote in the survey Statistician, we call this bias introduced in human beings, perceptual and perception bias. In this slide, you see the perceptual bias because I'm a perceptual, I come from perception, so we always work with perceptual things. The fact that we don't see straight lines here, whereas there are straight lines in the ground truth. The fact that we don't see these two tables are of the same size, whereas in the ground truth they are of the same size. We don't see these persons as being equally tall, whereas in the ground truth they could be equally tall if this building was actually strangely formed. And the fact that we sometimes see an Eskimo here and a face and another time tells us that the perceptual system is playing tricks with us all the time. And when we are going to use these the humans to annotate data, then we don't know for sure if the visual systems of those human beings who are annotating the data are actually playing tricks with us. So so somehow this is really a problem. Also, the perception bias, which is about the fact that people are living in a certain culture, have their own opinions about things, have their own values, make sure that they interpret things in a different way. than is plainly at their side. So somehow we are putting a lot of biases of people, cultural biases, but also perceptual biases. We are putting them in all in that training material. So the question that I would like to ask is, to what extent is the observed ground truth, and I put them between quotation marks, and how far is that real? I mean, it's strange that we just assume them to be real, but when you see how much we are influenced by our environment, by our visual system in interpreting things, it's really a good question. To what extent is the observed ground truth real? And when you start thinking about it, that maybe that it is not real, then you can actually ask yourself if a machine learning algorithm could ever outperform an annotator, because you are actually learning the machine learning algorithm, the mistakes an annotator makes, because of all these biases. So I started to worry about using machine learning algorithms when we are using human annotated data. And the main problem is actually this: how can we ever detect these errors which are introduced by the annotator, when the annotator is actually creating the training set, the test set, and in certain cases also a validation set? These are actually the same. These are actually data coming from the same annotators who are making these kinds of mistakes. So, so how could we detect these errors? In my opinion, if we stay with the humanly annotated data, we can never detect these errors. So we have to find different data sources to look at to see if we can say something about these errors. So the asymptotical behavior towards annotated data is about the fact that the machine learning algorithm will never be able to perform better than a human observer. And whereas we actually wanted to outperform humans, we wanted to make less mistakes, because that's the reason why we automate a lot of things in statistical processes, so that we don't have that human involvement anymore. But even now, when you use human annotated data, the weakest link is still the human in that process. So that's a problem. And I'm actually going quite fast, so take another sip. Then there is another important point, and it is actually about the representativity of training sets. And actually, this isn't about representativity itself. Well, it is, but the thing that happens at the moment that you don't have a representative training set for your machine learning algorithm, you actually, my statement is that at that moment you're not able to find the right features for your problem, this has to do with the fact that in some cases you have really minor classes, rare cases, and Piet will give some demonstrations on them. When you look at innovative companies and artificial intelligence companies in the Netherlands, these are actually rare cases. These are minor classes, and they have some features, but because of the fact that you don't have that many examples of them, you won't be able to find the right features. So it's something that is really comparable with what we see when making statistics. Our population is heterogeneous, is a big heterogeneous population. Each and every time that we are doing research, also when we do surveys, we are looking at a very heterogeneous population, and the way we overcome this problem within survey statistics is actually by stratifying the population and taking random samples out of that stratified population. We are going to make the the population more homogeneous by putting it by creating different strata and putting more homogeneous items within each and every stratum. And actually, this is also something that we could do with machine learning, and this is something where we are trying to start some research now in the Netherlands, where we're going to see if we could create such a population, such a sample, based on a stratified random sampling method. And the question then is, how do we find the right set of features? So how do you find the right set of strata? I'm sorry. First of all, you can use clustering techniques, like just normal machine learning techniques, where you say, okay, I have my my features, so I have my information about each and every item, and I'm going to see if I can find clusters which are much more homogeneous within that population of these features. You can also use background information, like we do in making statistics. But the goal is to find strata which are much more homogeneous, and to see if, when we apply that stratification to that population and get annotated data back, if we can actually do a better job in training those models. And there are different ways of doing that. You can actually use machine learning algorithms which have some weighing incorporated. So where you can just put a weight in your model. For instance, in logistic regression, you can just put a weight to each and every item that you train against. Or, and that's one I like much more, is use multiple models, one model for each stratum. And these are actually decisions we want to investigate in this piece of research. And something that is related to that is something which is called hierarchical classification. Suppose I have, for instance, a NIC, or maybe a code for goods. Then normally a machine learning algorithm will learn at the lowest level, at the leaves of the classification. So I have some text, and I know that one text is about 1.2, the other text is about 2.2.1, and the yet another text is about 2.1.1, and so on and so on. So we are classifying against the leaves. But what they are doing in this hierarchical classification is actually saying, okay, I have my complete corpus, and I'm going to classify the corpus first against the highest level of that classification. So in this case, 1 and 2. And after I did that, I'm going to take the ones that are classified for 1, and I'm going to classify them against, again, one level deeper. And I continue like that until I reach my leaves. And I'm going to use, if I can assume that I have real probabilities, and my ideal observer model shows that when you do it correctly, that you have real probabilities, then you can actually calculate the probability of an item being 1.1, 1.2, 2.1.1, 2.1.2, and so forth. So in that case, you can actually do your classification much better, and your models are really specific. So the models are much simpler when you use them, and they don't have that peculiar problem of inhomogeneities in your training set. So you won't be, even if the 2.2 set here is really small, it will still be able to learn about the differentiation between 2.2.1 and 2.2.2 because of the fact that the sets are much more specific. There are much less important features in there, and it will be able to pick up the small signals much better. So that's the thing I hope for when we are going to apply this also in a more stratified sampling method, so that we can get much better machine learning algorithms. Then my last part of the presentation is about explainable AI. One of the important things most of the statistical methodologists tell you that people should do before they are using machine learning algorithms is have an explanation why the machine learning algorithm is actually working like you want it to. And this is actually a very hard proof you have to give, because when you look at, for instance, deep learning algorithms, so deep neural networks, they are absolutely not explainable. You cannot follow from the input layer exactly what is happening to the output layer, and it's impossible for us to track it. Sorry. So somehow we have to find methods to make sure that we can actually explain those machine learning algorithms. And within explainable AI, there are actually 3 stages defined where you can explain an algorithm. You can start with explaining it in the pre-modeling phase. It's actually also the stratification of your data is already a sort of pre-modeling explanation. You are going to look at which clusters of data, which background information can be used to cluster the data in such a way that they are more homogeneous. So this is also pre-modeling explainability. And it is about understanding and describing the data. Then I will go to the post-modeling explainability. I'm sorry for the dog. The post-modeling explainability is about the fact that when you have a machine learning algorithm where you don't understand what is going on inside it, that you are going to define some experiments on that machine learning algorithm to actually find out what is actually going on in there. And this is actually the part where I, as a psychophysicist, got really happy, because these are the techniques that we also used in psychophysics. So what you do, for instance, is you say, okay, I'm going to take one variable at the input, or maybe a linear combination of variables at the input, and I'm going to vary them from a low value to a high value, that linear combination, and I'm going to see how the behavior changes of the algorithm. So what does it classify when that linear combination of those variables is low? And what does it classify when that linear combination of these variables is high? And how does it change when I gradually change it from low to high? And this gives us insight about why the machine learning algorithm is actually taking these decisions. So there's also a way you can deal with it. Another way, and this is the one a lot of methodologists actually think, is by explainable modeling. So only use models which can be explained. The good thing about it is that they exist. For instance, decision trees are really explainable because they take the decisions based on values of items which is in the data. So you can really you can just translate it into if-then constructions. So that's actually a very good way to explain your algorithms. But the problem is that when your data is getting more and more complex, these methods cannot be used anymore. And so for that, sometimes hybrid models are used, so that you use deep learning to find some sort of lower dimensional features, and finally you are going to use decision trees to make the final decision. And other methods can also be used for that, but it's hard, and in my opinion, you are making your life really miserable when you are going to only look at explainable modeling. I think post-modeling explainability and pre-modeling explainability already help a lot in explaining why the model makes the decisions. And then I come to a way I like to look at explainable AI. And it has to do with the fact that when the best way to validate a model is by understanding the model. And that's also a part of explainable AI. And this is actually the basis. This is where it's all about in explainable AI. You want to understand, you want to validate a model, and you are trying to understand why it is doing what it does. And Someone who formulated it already in '82 was David Marr, someone working in visual perception, a neuroscientist and engineer, who started to look in a different way at the human visual system. And he describes in his book Vision that there are 3 levels at which an information processing device should be described to be fully understood. And I will work from the lower part to the upper part here. So I don't start here at the upper side, but I start here at the lower side. And the first level is hardware implementation. He called it hardware implementation because he was looking at the human brain. And when you look at the human brain, then the platform you are working on is the human brain itself, or a computer where you are simulating stuff. He called it hardware implementation, but I would like to get rid of the hardware, and a lot of scholars also got rid of the hardware term. And it's actually about how is the algorithm realized, which implementation decisions do you have to make before implementing the algorithm. A level up, you have the representation and algorithm, the design pattern. This is what we normally do when we describe an algorithm. We have preconditions, postconditions, and we have some sort of description about what the algorithm does. But the thing is that a lot of these descriptions of algorithms don't explain why the algorithm is actually working in the right way. And that's the first level about the computational theory. How does the model relate to the reality? Why is it that this model is actually doing the right thing? And he formulates it in 3 questions. What is the goal of the algorithm, of the computation? Why is the computation appropriate? And what is the logic of the strategy? And this is all about how is this model seated in the physical world, in the ground truth that it is actually operating in. So that's actually the main thing that it is about. I learned a lot about it when I started to reread David Marr as a methodologist, and yeah, it's really a good book. So the computational theory Marr himself says about it is trying to understand perception by studying only neurons, in this case neurons. It's like trying to understand bird flying by studying only feathers. So, and he hits the point really well here. When I look at a feather, I won't be able to understand why the bird is flying. I have to see how the feathers are connected to each other and how they are moving in the air and how the aerodynamics is of those feathers to understand how the bird is flying. So you really have to look at the environment where those feathers are actually working in and how they are working together. So in AI, very often the how question is confused with the why question. So when I ask someone who made a machine learning model why the model is working, he actually answers the question how the model is working. And that's actually the main problem about the explainability. People don't go to the why question, they stick to the how question and tell me over and over again how it works. And for them it's fine. I mean, most of them are engineers, and engineers are trained to describe how something functions and not why something functions. So, but the why question is really important. Why are these features selected instead of how are these features selected? This is the right question. Why is it so that when I'm looking at for instance, innovative companies, why certain features are in there and some features are not in there? It's not the question how these features are selected. The question is why the features are selected. And then my final question to all of you, and maybe it's a good question for a discussion, is does it matter how complex the model is when we use such a strategy? When we use a strategy where we try to understand, when we start to ask the why question and start to understand why the system is working like it does. And in my opinion, this is all where explainable AI is about, explaining why the thing is doing what it does. And when you look at the original scheme that I had about explainable AI, then you see that there's a lot about engineering, a lot about technology, with a lot of things that I like in the pre-modeling explainability, but it's still a lot about the engineering part, and not about answering the question, but why is it that this model does what it should do and doesn't do anything else? So that's the main thing. And then I come to the conclusion, and I see that I did a great job again. So I come back to the quality of official statistics, and the relevance, the accuracy, the accessibility, the clarity, the coherence, and the comparability. And all of these questions have to do somehow with the subjects that I explained. Clarity with explainable AI, accuracy with the bias, and I can continue like that. And a lot of these things are not solved by machine learning engineers, by machine learning researchers, which are working in this field. They are actually looking at things that we also need, better algorithms to classify stuff, to do regressions in more complex environments. But they don't answer the questions that we need to answer. The question, why is it working like it does? How can I reduce this bias? What is actually the machine learning algorithm actually calculating, like I showed you with the ideal observer model? And these are all new research topics within machine learning that appear when we apply it to official statistics. And these are also topics that have to be solved before we can actually use these machine learning algorithms in official statistics, in my opinion. I mean, we still can use them, and Peter will show in the next talk how you can use them. But still, yeah, there is a lot of research to do, and with that, I would give the floor back to you. Thank you very much.
Thank you very much, Marco. First, for keeping to time, and also by presenting us such a comprehensive and challenging view of the potential for machine learning methods in the production for official statistics. We actually have good time for questions to be presented. So I'll ask the first person who posted a question, Diogo Cruz, I think, if he would like to open his camera and microphone to present his question. Diogo Cortis, I'm sorry. Diogo, are you there? I can't see Diogo. So I'll read his question. Nice explanation, Marco. That's a challenge in cognitive science. We study this phenomena as categorization problem. Depending on the problem, categories are more fuzzy. For example, we are working on an emotion recognition project in NLP. Annotators have difficulty categorizing more fuzzy emotions like disapproval, pride, versus simple emotions like love, happy. Annotators often don't even agree within themselves. If they annotate the same data point within 2 weeks, they usually do not agree even with their previous annotation. Would you like to comment on this one, Marco?
Yeah, I like the example, and if you don't mind, I will use it during my next presentation, because that's actually exactly what I'm talking about. I also have an example like this. When I still was in my PhD phase, at a certain moment, people from the Breast Cancer Institute in the Netherlands came to us with exactly the same problem, with exactly the same thing. In that case, radiologists were actually looking at mammograms, and when they found a micro-classification in them, they looked back at the image that was shot 2 years earlier, and they actually saw the micro-classification, whereas they didn't see it in the first place. The world is full with all these kinds of examples, and yeah, it is exactly the reason why I don't think that humanly annotated data can be used per se. So that you should that's actually the natural way to go. Try to find other sources for them. So I see that you agree, Diego. So it's yeah, I like the remark. Thank you.
Diogo, if you want to unmute your mic, you can make an intervention if you want.
Okay, our next question comes from José Antonio. José Antonio, would you like to make your question yourself?
Pedro, I'm sorry, but most of the audience cannot open their microphones, so we have to read them. Only the co-hosts and organizers can.
So I'll go ahead.
Now you can, excuse me, Pedro, now participants can unmute their mic if they want to speak.
Okay, but I'll read this one from José Antonio. Very nice presentation. A question about asymptotic behavior. You cited visual cognition, values, and cultural issues as sources of bias in data classification. And what about the behavior of people that today are already contaminated by the algorithms of digital world that induce these classifications?
Yeah, this is mind-blowing, actually, because from a traditional point of view, you always say okay, you have your population, and that population has some behavior, and you're going to measure the behavior, and you're going to model the behavior, and blah blah blah. But in this case, you have your algorithms again, who are actually in the middle of the population, are actually influencing the population again. It lets me think about one of the definitions we had on psychophysics. And I see that I have a lot of people here who know cognitive science a little bit, so or maybe even very good, maybe better than I do. Because I'm already out of that business for 20 years or something like that. But and it's actually something where someone asked us, what is it actually about? And one of the researchers said, well, it's actually about a very distinguished researcher, Jan Koendering, came with that remark. It's actually about the human being part of a environment. And two direction, bidirectional. So the human being who is perceiving the world around him and is also manipulating the world around him. And actually, this is actually what this remark is all about. We create algorithms in certain cases, and I'm happy that we as a statistical office don't do that already. We are creating algorithms in the world, which we are putting in the middle of a population. The models are actually trained on something. There are mistakes in there, classification mistakes in there, and you're putting back those algorithms back in the population, the results of them, and influencing your population actually to. It's even worse than what I was talking about in the presentation. I love it. Yeah.
Thank you, Marco. I will ask Marcelo Pita from Cetic to present his question. I think Marcelo can open his microphone.
Thanks, Marco. Excellent presentation. It's just a simple question, also about the annotated data bias and errors. Considering the perception bias that you talked about, the bias of the human classifier can be related to culture, to education, economic status, the humor of the day, and many other social variables. When classifying an object, a test, a picture, aren't these objects also filled with social aspects given by the producer of the objects? How can we deal with that? When will we be able to say that something is and something is not? So so everybody can agree in a classification.
Yeah, this is one of the problems your people noticed already from the beginning of artificial intelligence, and it's really a big problem. One of these cool examples that is used that you have to watch out when training a neural network was an example about a model that was trained by the American military to detect Russian tanks. And maybe a lot of people know this example, where the model was actually picking up the wrong thing, and they found out when they put it in the field and the thing didn't recognize any Russian tank. And the reason was that all the pictures that were taken of the Russian tanks by the spies were taken by rain, whereas the American tanks were actually taken by sunshine, because they were really proud about them. And you see already that there is a social aspect there in the collection of the data, and the fact that the spy in the field had to be very careful and liked it when there was a cloudy day, whereas the own pride is actually telling you that you should be demonstrate them in a nicest possible environment. And yeah, we always see stuff like that. For instance, the fact that that most pictures, when you are looking at pictures of objects and animals and stuff like that, they are taken with aesthetic rules. The question is the model not actually learning those aesthetic rules also? And what happens when you present a picture which doesn't apply these aesthetic rules? Does it still recognize what it should recognize? And what I was the pictures we are actually looking at are a lot of aerial pictures and satellite pictures where you don't have that cultural problem. So, but yes, you really have to be careful. Yes. Thank you for the nice remark. Yeah.
I have a question from Esperanza Magpantei. Thank you for the excellent presentation. Can you mention examples in official stats where machine learning and AI were tested? I think she wants to hear Pete's presentation.
Yeah, yeah. I'm sorry. I wanted to answer no, because Pete is going to explain them. So, yeah, exactly. You have to wait for after the break, and Pete will mention a lot of examples. So yes. Mm-hmm.
The next one is from Tiago Tavares. I'd like to share one recent presentation I did discussing the content moderation at scale and the role of IA/machine learning in NLP in the management of freedom of expression online. He gives the route for a PDF in the chat. Maybe you have some comment regarding this idea of moderation of content for sites which publish persons' comments or messages.
That's a difficult one to just give as a first shot. So yeah, I first need to look at. I already opened the slides, so
okay.
I'm happy to read it. So it's maybe we could get in touch and talk about it later. So
yes. I don't see further questions, but maybe I'd like to ask Esperanza if she wants to make a comment directly. Esperanza, if you can open your microphone and present yourself.
Yes, thank you very much. I just appreciated the presentation. I have nothing more to add. I will just wait for the additional information later on the examples. I just want to share that in the area of ICT statistics, we are also considering the use of machine learning and AI to sort of like estimate the data on internet use, so that any learnings from this meeting will be greatly appreciated as well. Thank you very much, and congratulations for the presentation.
Thank you very much. And if I would give a command back now, I would actually make Pete very angry because of the fact that I'm going to tell stuff that he's going to talk about it. So I'm not going to do that. So thank you very much.
Okay, folks. I have one last comment here. Let's see. This is, I think it's from Marcelo again. Marcelo, would you like to present your comment?
Just one more comment, and I would like you to comment about what I'm going to say. I've been in some meetings where people talked about the use of machine learning in justice. And there's a lot of issues about that. And you talked a lot about features we need to use: the observation, pattern recognition, the induction and deduction part. What about sometimes don't use some features because morally or ethically, we don't think they should be used and they should be placed in sentences in the case of justice? Would it be the case of race, ethnicity, gender, characteristics of a person that a machine learning algorithm may be judging, but they should not be used to do that? What do you think about extracting some features of the test set in order to make the judgment of the machine learning better?
Yes, that's actually something Peter and I have a lot of discussions with some people working machine learning at Statistics Netherlands. When you already see that some features are actually really about the thing that we are talking about, then start to use it. I actually have a very nice example, and I think I can just share the example. And it was about finding cocaine in containers which come from Colombia. And a machine learning algorithm came very fast to the conclusion that the cocaine was only in shipments containing bananas. And so at a certain moment they started to open all the containers containing bananas, and they didn't find that much cocaine in there. So and the reason was, when you look at the way those containers travel from the banana fields to the port of Rotterdam in this case, then you see that there are actually moments that drugs could be put into the containers during that travel, and it could be done in such a way that you couldn't recognize that container was open. And so you see that machine learning algorithms, we actually can only use them when they overgeneralize. And you see that in a lot of fields. There is a big affair in the Netherlands where people received money, which first they received money that they shouldn't receive. Then a machine learning algorithm, a data scientist, started to look at the problem, and at a certain moment, a lot of people were prosecuted for asking for the money without them being able to apply for that, and they received the money at the end. But yeah, and they were prosecuted for being doing bad things, but actually they weren't doing anything bad. But the machine learning algorithm overgeneralized to the wrong features, and that is what I mean when I look at how Marr looks at a perceptual mechanism, at a perceptual system, how it is in the middle of the real world. I mean, I can think about a very good machine learning algorithms which do a lot of good things with the data, which are able to separate the goods from the bad. But at the moment that I put it in reality, then it is a complete different story. And Yeah, that's a fact, and that's something data scientists really have to be careful about. So I think you are absolutely right. Thank you for the wonderful remark. That's yeah.
Okay, thanks everyone for presenting your questions, and Marco for the excellent and inspiring presentation. We will now break for 15 minutes. We will reconvene at 11:25 to hear Piet's presentation, okay? Thank you again, Marco.
You're welcome.
In 15 minutes.
Mm-hmm.
Well, folks, this is about time we re-engage for our workshop. This is my time to introduce the next speakers, the next speaker for today. I would like to give the floor to Piet Das. Professor Dr. Piet Das is a senior methodologist at Statistics Netherlands, where he leads the research on big data. He is a professor by special appointment on big data in official statistics at the Eindhoven University of Technology, where his work focuses on the development of big data methodology. Piet also teaches big data online at Statistics Netherlands, the University of Utrecht, University of Maryland, and the University of Mannheim. Piet, you have 50 minutes, and if needed, I will let you know when you are about 5 minutes before your time is up. And without further ado, Piet, the floor is yours. And okay. I apologize if I didn't say your name with the exact accent, but sorry, I'm not Dutch.
You can call me Pedro. That's the same name. I will share my screen. So this is the second part of the presentation, and it's a logical follow-up of everything Marco has told you about. It's about the application of big data in official statistics, and I will start by on the things we have learned on how to use machine learning, and we use machine learning in a much stricter way because of all the things Marco observed and talked about. We learned how to apply it. So I'll start with an example on how to use machine learning in official statistics. And this example is the use of the texts on websites for official statistics production. I will focus on the detection of innovative companies as an example, because we've done a lot of work on that. And I can show you how we checked everything and how we validated everything and how we stepped from induction and went to deduction. And then the next part of the presentation is on a number of applications of big data for official statistics, a number of the successes, and I'll end up, hopefully on time, with a list of 14 examples. So let's start with the example. A lot of companies have a website, and the idea we had is, can we use the text or the wordings they use on the website to determine if a company is innovative or not? And that's easy because that means we can scrape a lot of web pages. That's very easy. You can easily write some code that extracts the text from web pages. And we looked at the potential on how these web pages could be used, for instance, for the innovative character of a company. And that's interesting, not only for large companies, I will show you, but also for small companies. And this idea that we had means that we started inductively. We had an idea. We thought about it, and then we said, okay, let's start. And that means we have to start with data, and that means you start in an inductive way. And we see that gradually during our exercises, we will become more deductive. The interesting thing is that you need a high quality data set to do this. That's what Marco already explained, that it's very important. You need to start with the best input you can have to test this idea. The interesting thing is that in Europe, there's a community innovation survey, the CIS survey, I will call it in the remainder of this presentation. And that's a survey that's European standardized. So it's sent around in a lot of other European countries. They use exactly the same questionnaire. And the questions are focused on determining the innovativeness of a company. And in the Netherlands, it's sent every other year to a sample of 10,000 companies. The very large companies always get this questionnaire, but there's somewhat smaller companies, that's a sample. And those companies, to have to be included in this survey, need at least 10 or more working persons. And that's a very important thing, because our idea is to use this questionnaire. But the thought occurred prior to this that it would be great if we can develop a method that could also be applied to small companies, such as startups, because that's where innovation starts. Can we develop something that can be applied not only to large companies, the companies with 10 or more working persons, but also to small companies? That's the information we have. So we have the response of the sample for the CIS survey. So we can use that in our training set, but it's essential if you use a website to be 100% sure that that website is the website of that company or you have sent a survey to. So we needed a link to the website. And fortunately, in a European project, they developed the URL search approach where, starting from the name of the company and some additional information, you can look up the official website of the company. But to be absolutely sure, we did lots and lots of manual checking. So of the response of the 10,000, we checked every response to make absolutely sure that we have the correct website of that company prior to starting on this, which was already a lot of work. So that means we have a good start. You can certainly call this a representative data set, at least for the large companies, because it's a sample used by a statistical office, and we have the response of that. And we made sure that the link between the unit and its website is completely checked. So that's a good point. Then we scraped the data, extracted it, and created a machine learning based model. So we transformed the text into features that we developed a model on. And after doing that, and I won't go into much detail here because it's a demonstration of how you can use machine learning, we ended up eventually with a model that was able to classify the websites of the companies with an accuracy of 88%. So 88% compared to the results of the CIS survey. So that's fairly good. And we did that by training it on an 80% random sample. So you have those, the response of the 10,000 companies, 80% of that is used to train a model, and 20% is independently used to test it. And the test result was 88% accurate. And the ratio of positive and negative examples in our training set is comparable with those in the CIS survey. So that should all be okay. But we made some choices during developing a model, and those are important to mention because I will come back to them later. We found out that there are a number of companies that have websites with hardly any words. They have great movies on that, but there are not a lot of words there. And if you have only a few words on a website, then you can't really build a reliable classifier on that. So websites with less than 10 words were not used. So we only used websites with 10 or more words. And we did some standard pre-processing. Anybody familiar with text mining will recognize these. And anybody not will quickly learn what the standard approach is. Now you remove any stop words because in principle they are not informative, certainly for this task. You removed all numbers, any punctuation mark, and very small words were removed, and we removed also several other words later on, which are, it's interesting looking at the question and the discussion with Marco. So the model was developed. Oh, great. The fact that it's 88% accurate means that there is a relation between words, particular words used on the website, and the fact that the company is innovative according to the classification results on the CIS survey. And you can look inside the model and see what the words with the most important weights are. So the positive words with high weights in the model. And this is the English translation. In principle, a website in the Netherlands is usually in Dutch, but there are English websites as well. And we tested it, but we decided to develop a single model for any language in a website, which is either Dutch or English. These are the translated words. The com is the most word with the highest weight, which is indicative for a company. System, inspiration, data, technology, and analysis are clear examples of things that certainly indicate an innovative company. Do is a bit strange here, but that happens if you use machine learning and you throw in lots and lots of words. Apparently, it has an association with the word do and innovative companies. And also the language is important. The model adding language as an additional feature really improved the performance of the model. And it indicated that if a website is in English, then the company has a higher chance of being classified as innovative. So, and that's something you would expect. An English-oriented website means a company that's not only oriented in the Netherlands, but also to other European countries. Now we have innovative companies, but we also have non-innovative companies, and clearly non-innovative companies is a very diverse group, and that's shown in the words as well. But if you look at the words, it suggests those are mainly companies that sell products or are regular shops. So sale, buy, powered, shape, exclusive are all things that appear there. Create is a bit strange to be included as a negative word, but apparently it is. Perhaps it's used by a lot of non-innovative companies and sort of acts like a buzzword. But this gives an indication on the first idea, you're starting to validate what your model is actually doing. You try to interpret what's going on. And overall, it seems to make sense what the words that the machine learning model is picking up. So we did our first validation after checking the model. So we decided, okay, we have developed the model on a small, limited set of large companies. Let's scrape everything, because at this point in time in the Netherlands, we could link a lot of the websites to the companies in our business register. So we were able to scrape a lot of the websites of the large companies, and they were excluded from our training and test set. So this is an independent check. We scraped around 37,000 companies, and we classify them. And I'm showing a plot here with the chance of being innovative. So instead of a classify using it as a negative, as a non-innovative or an innovative company, it produces a number between 0 and 1. So it shows the chance of being classified as innovative, although you might discuss if it's an exact chance. But the plot that came out of it, so by classifying the 37,000 companies, had a nice U-shape. So I was really happy when I saw this. I thought, wow, it's a U-shape indicates a clear group on the left, the non-innovative companies, and a clear group on the right, the innovative companies. In the middle, there are companies that are classified with a value in between 0 and 1, but it's clear that there's that the model is able to clearly separate those two groups, and that looks really nice. This is something you would dream of, but in a perfect world, the values in the middle would be a bit lower, but it's nice. So really, all things look very promising at this point in time. And then that means our idea seems to work, at least for the large companies. And then, but you're still in sort of in the inductive part of your process. But then you have the theory, could the model be used to detect small innovative companies as well? So could we generalize this? This is the start of deduction actually going on here, because you develop a hypothesis. So you're stepping out of your inductive cycle, and you ask yourself the question, can it be more generalized, this approach we have? Because that is what you essentially want as a statistician at a National Statistical Office. So deductive reasoning kicks in here. Okay, let's do some quick tests if that model would work. The easiest and interesting test you can do if you look at small companies is look for small companies that are probably have a high chance of being innovative. And we looked at startups in the Netherlands, and there are lots of websites that contain lists of startups and their associated websites. So we scraped a set of 900 websites, throw them in the classifier in the same way we process all our data, and we found that 92% of them are innovative. So I thought, that's nice, because that means our original model can also be applied to detect innovative small companies, and to make sure that not every small company is classified as innovative. We also looked at the websites of small companies included in the Dutch Business Register with a linked website, and we classified them as well. And there we found that according to our model, 33% was innovative. So clear, there are different groups of small companies here, and our model is able to discern them as well. So we had a nice external validation, again, showing that this approach seemed to work well. So clearly, this indicates that in general, there seems to be a difference between the wordings used in the websites of innovative companies compared to the non-innovative companies in the Netherlands. So the funny thing is, if you have a huge amount of data, you can create lots and lots of nice visualizations. So we had classified, essentially, we have linked every company in our business register with the accompanying website, at least for whichever possible, if they have a website. We scraped all those websites. So let's make a map of where the location is of all our classified innovative companies. And we can link them at the municipality level, because we have the address information, but also at the zip code level. At the municipality level, and I'm sure not a lot of people are familiar with the Netherlands, but this is how the Netherlands looks like. And there are clearly large bubbles on this plot, and large bubbles means lots and lots of innovative companies located in this municipality, and the largest bubble is indicative of Amsterdam, the capital of the Netherlands. And if you compare that number, the number of innovative companies, compare that to the number of inhabitants or people that live in Amsterdam, or the number of businesses, it's clear that if you look at other municipalities, that a much higher number of innovative companies are located in Amsterdam than in the other municipalities. So clearly Amsterdam is a hotspot regarding innovation. But it also shows a lot of other locations. And if you look at the ratio between the number of innovative companies for different municipalities, and especially for municipalities that have universities or an applied university, then the number of innovative companies is clearly higher than for the other municipalities. So again, a confirmation of the idea that our model is really picking up something indicative of innovation. And especially for Amsterdam, because we have so much information, you can even create a more detailed map. You can create a map that's indicates the number of innovative companies at the zip code 4 level. That's essentially the most detailed level we are allowed to publish in the Netherlands. And zip code or postcode areas that are clearly brown in this picture of Amsterdam means that there are lots and lots of innovative companies there. And these areas are known to inhabit startup incubators, organizations that support startups in the initial phase and say, okay, you can come into our building and have a room there, start working on your innovative ideas. So they are essentially hotspots in a municipality. And that's picked up by a model. And even at the most detailed level, it still makes sense. So that's again supporting the idea that our model is really picking up something associated with innovation. So that's great. Then you come to the next hypothesis, because you want to test it more and more. If you have a model and if you can identify the number of large and small companies in the Netherlands based on that text, can you use that model to estimate the number of large companies? And for the large companies, we have an official statistical publication. So we know what that publication says about it. What will happen if we use the model to do that as well? We used and we try to include as much companies as possible. I'm a really somebody who likes to do census-like approaches, because it's all about big data. Try to link as accurate as possible all websites to all businesses in the business register, and then estimate the number of large companies first, and then the number of small innovative companies. We had around 850,000 websites linked to the companies in our business register. So let's do that for the large companies. But if I would show you the exact number of businesses classified, the number of large companies, that's not the number you should look at, because we know that the model has bias. That's what Marco told you about. So we need to correct it for the bias. And where we looked at was an approach developed by a colleague of mine, Quinten Mertens. He wrote that down in his PhD thesis. Because in principle, the model is 88% accurate. That means 12% is misclassified. And the misclassification from a machine learning perspective is always of either a false positive or a false negative. A company that's innovative is classified as non-innovative, and the other way around. If the ratio between the false positives and false negatives is identical, then there is no issue. But our model has a tendency to slightly overestimate or to slightly produce more false negative than false positive. So we need to correct for that. And our colleague Quinten has developed a method for that. So we applied it. That means the number of innovative companies increases. Then we had to include an estimate of the number of innovative companies that had websites with less than 10 words. We very detailedly looked at those websites and those words, if they were really different from, if there were specific subgroups in those in those groups of websites, that was not the case. So we decided, okay, that will probably then be the same ratio as in the websites with more than 10 words. So that means an increase in the number of innovative companies again. And because we had a CIS survey and because we manually checked if the correct website was found or linked to the correct business, we also found that there are a very small number, but there is a small number of innovative companies that doesn't have a website. And we also checked that for small companies as well by doing a small phone survey. And in the end, we estimated that the number of innovative companies without a website is 0.01%. So that's a very small amount, but it's something to take care of. If we correct all that and combine all the information for the large companies, what do we end up with? The CIS survey in the Netherlands says 19,916 innovative companies, plus or minus 680. That's the confidence interval here. And for the web-based text estimate, we end up with 90,276 innovative large companies, plus or minus 190. We did a bootstrap method to determine it and repeated the whole procedure 1,000 times. If you look at those numbers and look at the confidence intervals, it's clear that there's an overlap between those numbers, and essentially means that we're able to replicate the findings of the CIS survey by looking at website text, which is great. And I thought, okay, that means we've proven everything. But then we ended up with quite a lot of discussions with colleagues, is everything was correct or not. But in principle, this shows that looking at the websites and the text is a great way, an alternative way to obtain information that you could without sending a survey to a company. And we, in principle, classified every website that was linked to a company. If you look at the number of small innovative companies, and there is no official number on that in the Netherlands, our web text-based method says 33,599. But that's only for the companies with 2 or more working persons, up to the number of 10, because if it's larger, it's included in the CIS survey. Why do we focus on the larger ones here? Because we saw some odd behavior. If a company has 1 or less working persons, so that's what we call self-employed or semi-self-employed companies, then the U-shape we saw for the large innovative companies, we saw that for the innovative companies with 2 or more working persons, but for the smaller ones, there was a clear peak around 0.8 included as well. So clearly this group differed from all the other examples. So that means that this also indicates that model might be off here. And because of this odd behavior, we decided, okay, let's only focus on the companies with 2 or more working persons, because that seems, those companies seem to have the same behavior as the large companies. The semi-self-employed didn't. So there was a clear issue there. That's a downside of applying the model. But you can even ask a more general question. If we have a model and it seems to work well in the Netherlands, and there are lots of pluses here that it seems to work well, could you apply this approach also to detect innovative companies in other European countries? Because the CIS survey that we use is a European standardized survey. So wouldn't it be great if you could apply this to other countries as well? So that's another validation. And in principle, when we wrote this down during a literature study, we discovered a paper of Kina and Lenz that was eventually published in 2019, where they describe a very similar approach. They use the text on websites of German companies to determine if they are innovative or not, which means you can already, this has already been done in Germany. So that's another example of something that indicates, oh, website texts are very informative. We had an intern in Flanders, Statistics Flanders. Flanders is the upper part of Belgium, where in principle they speak the same language as the Dutch people do. And we assisted them in their research, and they essentially confirmed that also in that part of Europe, text on websites can be used to determine if a company is innovative or not. So that's great. We thought we had an intern as well, and we had a good cooperation with Sweden. So we decided, could this intern develop such an approach and test such an approach in Sweden as well? And he was able to do that. But our results were not confirmed. So in Sweden, clearly the behavior is different, and which annoyed me a bit in the beginning. But if you think about what you're actually doing, you might try. You probably can understand why this happened. But in Sweden, purely coupling the approach developed for the Netherlands didn't work. At least the accuracy was 0.7, so 70%. But that wasn't high according to our standards. But there is clearly a signal in that data indicative of being innovative, but you couldn't apply it in the same way as in the Netherlands. So we need to realize it, because I'm very positive about what you can do with it, because you can estimate the number of innovative companies, small innovative companies, without sending them a survey, without annoying them, and you still have an idea how things are doing, and you can produce very detailed, obtain very detailed data at the municipality level. And there's a huge interest in the Netherlands also to see if stimulating innovation or stimulating startups by certain measures, if you're able to use this method to test if that really helps or not. But we still need to be aware of the fact that we're not directly measuring innovation. We are measuring the association between the presence of certain combination of words and the classification of innovative and non-innovative companies used in Europe. And clearly, this relation can also be used to detect small innovative companies in the Netherlands. But this relation is essentially depends on how a website is used by a company. And clearly the behavior of companies in the Netherlands, the upper part of Belgium and in Germany, shows that this can be done. Apparently, how a website is used by an innovative company and how the words shown on the websites are used is something that you can capture with this model and that you can use. But apparently the results for Sweden indicate that it's not always the same for each country. It might be that in Sweden websites are used in a very different way than what we are doing. And that's an important point here. We have to realize that we're not directly measuring the thing that we want to do. And here it's nice to quote Mar, which was included in the presentation of Marco. Try to understand the nature of the problem being solved, what you're actually doing here. And if you're so focused on analyzing data and scraping websites, classifying models, you sometimes forget the why question. So, but it shows you that if you're very careful, you can start in a deductive way and do all kinds of checks and eventually end up in a deductive way of working, and you're still able to use all the experience you have to develop a model that has very interesting promises for the use in official statistics. But there are more, and I will talk about some other examples now. One of the examples that I'd like to show you, the second example, is an approach very similar to what I just told you about. It's again using the text of websites, because this was a question that was actually asked to me in the beginning of the COVID period. Pete, based on the experience you have with detecting innovative companies, could you develop something similar to detect platform economy websites? And I thought that's great. Let's try and test it. And just for the sake of argument, it's important to know what is exactly a platform economy website. In principle, it's stated that a platform economy website is an online platform that mediates or supports the exchange of goods, services, or information between individuals, companies, and others. Examples: Airbnb is a great example. People have a room to spare and they want to rent it to other people, and there are other people that would like to rent it. People, Airbnb supports that. That's a platform economy, and in principle, the department responsible for that wants to identify as much platform economy companies as possible by looking at their website, and then from that information determine the turnover. So what we're looking at is, can we use the text on the web pages to detect platform economy websites, just to pre-screen the population of Dutch companies and identify the companies that have a high potential of being a platform economy website? If that's the case, those will be sent a questionnaire that they need to fill in. So this is at the beginning of the statistical process. We did that. They provided a set of examples of platform economy websites, and actually they found 680 positive examples. And this is usually what happens in our office. Somebody wants you to build a classifier, and they give you positive examples only, and it is a bit strange. Fortunately, in this case, a few negative examples were given because they said, yeah, we tried to do some selection, and the set we have, the majority of them were platform economy websites. Some of them really resembled them, but they weren't platform economy websites. And that's great if you try to develop a model, because in principle, you have examples that are really clear examples and positive examples of platform economy, and a few really resemble them, but are not. And then I just added a random sample of non-platform economy websites from the business register. Just draw a random sample of from the business register, look at those websites, make sure there's not accidentally a platform economy one in there. And I ended up with a 50% positive and 50% negative ratio, just to check if there is a difference between those websites, and if it's in the same ratio, at least there's a random chance of classifying something positive or negative. So any higher than 50% means there is some signal in there that you could use. So we developed the model, tried some standard pre-processing. We found out here that we need to combine the information on multiple web pages per website. So we scraped a lot. And in the end, we ended up with a support vector machine with an accuracy of 82%. That was the best option available. It's not perfect. I always try to aim for higher, but if you're pre-screening it, using it for a pre-screen method, then I thought, okay, this is the maximum we can get out of this approach. And that should be okay. We tested it. The model provided a chance of being a platform economy website. It was a small test set, but it showed some U-shaped distribution, so could be okay. You need large amounts. Preferably you need to classify large amounts. And I will show you a distribution later on. And there are obvious words positively associated with platform economy. Register, com, again, com from commercial, company, login, platform. That's nice if the word platform is in the top 10. Invest, sign up. So it means a website where you need to become a member or something like that. So you need to register at least. So that makes sense. And the negatives are a lot of other types of websites. So I'm not going to show you here because they're a mixture, but the positive words seem to point into the right direction. So that's very nice. Then we applied that model to every website we have scraped that was linked to companies included in the business register. And then something very strange popped up. If you have around 850 websites, and this is the probability of being a platform economy website, there's a huge peak close to zero, and a very, very small amount on the right side, which is the chance of being a platform economy website. So it's really skewed that the majority of the companies are obviously non-platform economy website. It's not the same distribution that was seen by the innovative company stuff. And if you zoom in on this small part, then you can see there is a small peak there, and very close to a value of 0, actually around 9.5. So up to 9.5, you can see that the value starts to increase there, which suggests there's some subgroup there that might be indicative of platform economy websites. And we're suffering from the effect that Marco showed you earlier. We've developed a model on 50% platform economy and 50% non-platform economy, but you had no clue how this ratio was in the actual world, in the real world. And it's clear that platform economy websites are not the majority of, it's the other way around. There's only a small part of all companies in our business register are platform economy websites. And we actually also applied the model developed by Marco to compensate for that, which means we end up with a smaller amount of companies that had a high chance of being a platform economy website, but they still included some false positives. But that's not the problem. It's great to use it as a pre-screening method. So we found that quite a large number at our potential platform economy if you assume the cutoff value of 0.5, but you shouldn't do that. That's what Marco taught you in the earlier presentation. And we did a lot of manual checking. Websites with a value of above 0.8 were found to be more interesting. They also contained some adult sites and some sites with not a lot of text. They were removed because we want to make sure that we focused on the correct websites in this case. In the end, we ended up with 5,700 websites, which were linked to a bit more than 4,000 companies. And by carefully looking at them, the experts decided, okay, the 3,522 companies are really interesting. They all received a survey. The response was fairly okay for the current standard. So more than 2,000 companies responded, of which 537 were really identified as platform economy websites. And the interesting thing here is you have a machine learning based pre-screening that you do. You send them a survey and receive from those companies information that you can use to identify them as a platform economy website, and you can combine it with the chances that you had obtained. Yeah, and based on this, it was found that platform economy companies all had a websites with a value above 0.95, equal to or a value higher than 0.95. So this really demonstrates that this text-based approach is a very good way to pre-screen it. And we actually applied this model this year again, and we can confirm that the model is stable, and it's reused now to again pre-select platform economy websites and send them a survey. This work was done by an intern that really did great work, and I was really happy with this finding because finally we had another data source that we could use to confirm our text-based machine learning approach. So that's nice. This is one example. But there is a big data source that a lot of people already know, but they might not think about that being a big data source, and that's scanner data. And in a lot of countries, they increasingly use scanner data to obtain prices for products that are used to create the consumer price index. And in the Netherlands, all data is obtained from secondary data sources. So we don't use surveys anymore. There are no people going to shops and writing down prices. Everything is used from either scanner data or obtained via web scraping. Scanner data is a data set obtained in the beginning from supermarkets. So every week, at the end of the week, supermarkets sent us aggregated data that contained information on the number of products sold, their codes, and the price of the product. So how many bananas were sold in the Netherlands and how many things. And that's used for the consumer price index. But because you receive such data sources every week, you can do all types of analysis, and you can use such a data source also for new types of analysis. For instance, to gain quicker insights, and especially during COVID, it was interesting to see what kind of products are being sold certainly in the beginning of COVID, where we had essentially had a lockdown. What are the products sold the most at that point in time? Usually it's bananas in the Netherlands in supermarkets, but something changed. So there was what we call hoarding happening during the pandemic. And these analyses, they were also published on our website. And it was clear from this data that there was a run on rice, which you can store a lot. It's food and you can store it a lot. Hand soap, obviously, and toilet paper. The same thing happened in Germany, if I recall well an anecdote of Marco about hoarding toilet paper in Germany. And this is just an example to show, because we have a regularly delivery of these kind of data sources, you're able to do all sorts of additional one-off analysis to get more insight on what's going on in society. And this is a very interesting one that's been published during the Corona pandemic. A big data source that obviously should be mentioned, and I've talked a lot about it together with Marco on the work that we did in the beginning of our big data period, is road sensor data. And road sensors in the Netherlands are essential, either loops or cameras that count the number of vehicles passing at certain location in the Netherlands. And this was a great data source to start working on big data in our office, because it's a huge amount of data. At that point in time, there were 20,000 sensors on the Dutch highways alone. So that excludes all the smaller roads. Those are the highways. And they're very different type of sensors, but all the data is available for every minute of the day, 24/7, 24 hours and 7 days a week. And this is the Netherlands and the highways, and essentially all the roads are covered. If you create a plot of that, you can see that a lot of those roads are fully covered with sensors. So we have a huge number of sensors. Well, there are some roads that have less sensors, and there was even a road that had sensors, but apparently was not included in the original map we showed here. And it's data that's quite noisy as well. It contains errors and there are mistakes in there, and sometimes the sensor doesn't work. So it produces all the kinds of interesting profiles in which you can see in principle. If you look carefully, you can see the whole week. You can see the working days, the 5 days where you have a morning and an evening rush hour peak. I can indicate that here. And in the weekend, the behavior is very different. And you can see a single sensor might occasionally fail, but there's always another sensor in a few kilometers lying ahead where you can use the data from as well. And it's also clear that the data can be very noisy, can be very erroneous, but sometimes looks really, really well. And we use the data to create a traffic index in the Netherlands. And I'm showing you the first part of this series because it really shows that when the new year starts, there's a real dip in the number of vehicles on the Dutch highways. That's because everybody's at home, they're enjoying the holiday. But this plot also nicely shows that in the beginning of this series, the data looks a bit odd, and that's because the roads were not really well covered with road sensors then. So we didn't have a lot of sensors on the road. And this also indicates that if you have more sensors, the data becomes better and better. And this is a very nice plot, and I have very nice memories on the work we did here. A fifth example of use of big data in official statistics, and I'm very proud to tell you this because we're actually going to produce an official social media based statistic very soon, and not an experimental one, but an official one, is the use of social media. This is usually the most difficult big data source you can imagine, because social media, it's interesting, but there's only a small part of the population active on it, and that probably is a selective part of the population, and you can only use publicly available measures. It's a lot of work to collect it, but fortunately there are commercial companies that do that. And in the Netherlands, we closely cooperate with a company that collects all the data. So in principle, certainly for Twitter, we have all publicly available messages in the Netherlands. And for some other platforms, we have a large part of those messages. We did a number of studies. We had some great findings. The best findings we had was the general social sentiment indicator that we developed and clearly correlated with consumer confidence, but I'm not going to tell you about it. I'm going to give you some short examples of the social tension indicator, and the social tension indicator is going to be published in fairly soon, and some examples of some COVID studies that you can do with social media, just to give you an idea of the possibilities you have with these kind of data sources. Social tension indicator is started as an example of something that we wanted to measure. In principle, we wanted to measure the safety, feelings of safety. We have a survey on that. And we had the idea, could we use social media to detect safety feelings online or feelings of unsafety online? And if it's nearly real-time available, it's also something you can experiment with, a real-time indicator or a daily indicator. And that you could apply that to Twitter as well, because it's obvious that on Twitter, people really want to be the first to report some interesting news. So if that news is related to feelings of safety or unsafety in our country, can we use that? So we we started in a very traditional way. We interviewed people and asked them questions on the types of words they use to express feelings of safety or unsafety. So we end up in the end with a list of around 350 words associated with safety and unsafety. And then we start looking up in the database we have access to from the company called Cousteau, how often these words occur. And we found out that only 150 of those words are used frequently online, which is an indication that the vocabulary on social media is much poorer than on in real life. That's my impression as well. But that means those 150 words could be used to count the number of messages containing those words, and the sentiment of those words could be used to determine if they feel safe or unsafe. And we also found out that because we essentially use the same language as the people in the upper part of Belgium, Flanders, that we need to remove those people as well. So you have a sort of a mixed population here, and we try to reduce the number of messages from outside of the Netherlands as much as possible, because we want to measure the situation in the Netherlands. And then a very interesting profile occurred, but we thought, and there were peaks in there. Are we measuring? What are we actually measuring here? Are we measuring feeling of safety or unsafety? And we looked at the peaks, and we found out that peaks occurred when there were. Yes.
Quick interruption, just to say you have another 5 minutes. Okay.
Yeah. Okay. I'll round it off as quickly as possible. So we what essentially did is that we started with the idea of measuring safety or unsafety, but because we only had a limited number of words that are used, we checked what those peaks actually represent. And we found out that they're not measuring safety, but they're measuring social unrest. People are sending out messages that something is wrong in society. And eventually we called it the social tension indicator. It was tested for a year together with the police and the Ministry of Justice. And we thought it was okay. And the interesting thing is, if you have peaks, you can click on them and you can see the topics and the words used by those people. And it gives you an indication of the event that they're reacting upon. And then after a year, we decided, okay, the project ends and now we stop. But at the moment that we pulled the plug out of this indicator, the police and the Ministry of Justice started calling us. Yeah, we really need the social tension indicator because it's an important indicator used to report to the Dutch government. So we're now making sure that it becomes an official statistics, and it's something completely new to compare what we have already done. You can also do stuff on COVID. We developed an indicator that's able to detect the sentiment on COVID. And Marco has done very interesting work on if you're able to detect people with COVID symptoms on social media. And if that increases, that's an indication of, in this case, the second corona peak. So you're able to nearly real time measure the spread or the people that are infected by COVID by using very advanced modeling stuff. For the people that have access to this presentation, this is a list of all big data uses for official statistics, at least in Europe. It would be great if you have other examples to include them here as well, because I'm trying to get an overview of all possible applications of big data for official statistics. The first two are in production, the third will become in production, and the rest is all in the implementation or experimental phase. So thank you for your attention. Big data is a very interesting potential application for official statistics. And I will stop here, because otherwise I'll stop talking.
No, that was excellent, and apologies, you still had another two or 3 minutes, but
yeah, it's okay.
It's okay. You can cover up during the questions. I will now read one question we have on the chat, maybe one from Ana Gabriela Faria. Great presentation. How did you represent the tokens? I think she asked this during your presentation on the identification of innovative companies. Mm-hmm. And did you use word embeddings or a sparse matrix? That's probably a very technical one, but
yeah, I'll try to explain it as simple as possible. In principle, I didn't mention that we use word embeddings, but in principle, you start with the text from the web pages, and you know if that text corresponds to a innovative or non-innovative company, and then you look in principle at the occurrence of the words. I use a TF-IDF approach there, but we found out that that didn't contain all the information you want, and you can use word embeddings if you look at text to extract extra information. In principle, that's the combination of words, how often combination of words occur on the website. and that really geared up our accuracy. So it's part of our model it is trained on the combination of term frequencies, as the TF-IDF, and the word embeddings as well. And that's used to develop a model. And the interesting thing is that points to a difference between Sweden and Flanders and the Netherlands. The word embeddings model for Flanders, developed by the student, was different than the one for the Netherlands. And that's something we didn't change for Sweden. And probably the word embeddings is an essential part of the model, and there might be a need to develop a specific word embeddings part for each country, because the way words are used or in combination might be different for different countries. So it's a great question. Yeah.
Thank you. I have another one. Congratulations. This is from José Antonio. Thank you to sharing these interesting examples. In the first example, you mentioned the risk of indirect measurement, but does the model somehow consider the possibility of false innovative image on the pages fueled by the search result itself?
Mm-hmm. Yeah, that's a challenging question, because I'm trying to interpret what that person actually means. But what it does is by at least you can correct for the fact there are some false positive, false negatives in there, and that's something that you can capture, because in principle you want to estimate the number of innovative companies. We tend to look at this and say, no, every website should be correctly classified, but in principle the goal of a statistical office is to get an estimate of the number of companies, and that doesn't mean that everything has to be exactly correct, but overall the number should be okay.
Thank you.
I hope that answers the question. Otherwise, just contact me again to explain what you actually want.
We have one from Amar Marine. In your experience of big data and ML, do you start with the finer criteria for the research question as the traditional methodology? I'm not sure I get the full meaning. Maybe Amar could get online and present the question.
Yes. Hello, congratulations.
Hello.
So by coincidence, I'm editor-in-chief of International Journal of Medical Informatics as well, and I received several articles from Netherlands, and I know several people from there. And one big issue with the eyes on the healthcare, I know you have a very nice data set. It's called NICE in Netherlands that collects all ICU, intensive care unit, and all COVID. But finer criteria, it's when we start a traditional research in healthcare, and it stands for it's feasible, the data we have, it's interesting, it's novel, will bring some new knowledge, it's ethical to use all those data, and it's relevant to create some outcomes for the human being. Because, there is a lot of machine learning methods and papers in healthcare. They don't explain the results. So how reliable it's to adopt an automated prognostic, for instance, in COVID, in ICU. And we are using a lot of big data and machine learning. But in your experience, how can you rely on those models?
Yeah, that's a great question. Yeah.
Thank you.
In principle, a lot of the answers are already indicated in Marco's presentation. You have to look very carefully at the model, but I can give you a great example. That's something I mentioned in the beginning. We developed the model just to test the idea, to see if there's a relation between the text on a web page and the fact that the company is innovative. And then I mentioned that we removed some words. And the interesting thing there is that we discovered that we were somehow picking up a link, an association with innovative companies with the month of July and non-innovative with the month of August. And we scraped the web pages during the period of July and August. So apparently we scraped more innovative companies in July than we did in August. And that's not something that you want to pick up by the model. So you're constantly checking what the model is doing and see if it makes sense. That's why you're testing stuff. That's why you're looking at the words with the most positive weights and the words with the lowest weights, just to make sure that it makes sense what you're doing. And that's something that you should always do. And it's in the nature of a lot of scientists. But if you want to have quick results, you can just apply a model and say, okay, this is it. But then the real science starts. That's something people forget. And that's what Marco also wanted to point out in his presentation. So that's a great question. Yeah.
Thank you.
Thank you very much, Piet.
Mm-hmm.
I don't see other questions in our chat box. You may have one more minute if you wish to send in your question.
Yeah, the previous question that you asked me that we both didn't really understand, Marco made a remark on that, and that has to do with the fact that at the moment that you, again, relation between text and innovative companies, the over time you could expect that the wordings used on those websites might change. Innovation starts. 3D printing might be a great hype now, but it isn't over in a number of years. It might be something else. So your model should be able to deal with the dynamics in the world, the way people use a website or the way people use social media might change, and you should always check if the original assumptions you made in the beginning and the original data set on which you developed data, if the model is still applicable on the current situation. This is something that you call concept drift. Are you measuring the same concept or is it drifting away? And that's something that we work on as well, to make sure that we are still measuring what we think we are measuring. That's an important point.
Yeah, that's excellent. Thank you very much. I don't see any new questions, so this is time for us to bring the session to a close. I won't do that. I'll hand it over to Alexandre for that role. But thank you to you and Marco again for excellent, inspiring presentations. Congratulations on this huge amount of work you guys are doing in the Netherlands on this topic. We are all eager to learn more from you over the coming months and years. And well done, excellent. Thank you very much. I'll hand over to Alexandre now for the closing of the event today.
Thank you very much, Professor Pedro. Thank you for your excellent moderation. And a big thank to our speakers, Marco and Pete, for the excellent and inspiring presentation. You gave really very good examples and applications. And I'm sure that it was a huge contribution to the data community, not only in Brazil, but in Latin America and abroad as well. You know that the main objective of this series of workshops is to put together data producers and data users so that we can really create a new ecosystem. And I'm sure that we are building a new data ecosystem with new data sources, new methods for data collection and data processing and modeling, as both of you have explained it. So the future of data production is a mixture of different methods and data sources. So thank you really very, very much. I hope that you will remain our contact for next year edition. And I would like to invite all of you to come back tomorrow for our last day webinar. Tomorrow we will have a session on international projects on AI. We are going to have speakers from OECD, from UNESCO, from the International Research Center on AI, IRCAI, which is a Slovenian center. which is a UNESCO Category 2 center, just like Cetic. We are broader type of centers, and also representatives from the Center for the Fourth Industrial Revolution. So these international organizations will share with us tomorrow, will showcase their initiatives and their projects on AI, and of course, the importance of measurement, of having proper indicators and statistics to measure the adoption of these technologies, and of course, to measure the impacts in society, in business, industries, and governments. So please do come back tomorrow at the same time. You can use the same link for our last day of this year edition of the NIC.br Annual Workshop on survey methodologies. Thank you very much. Wishing you a good afternoon in Europe and good morning here in the Global South. Thank you very much.